Hi everyone. Until the last lecture, we have learned a way to formally describe semantics of program, which is called operational semantics. That is really similar to the actual machine's behavior and actual machine's operation. Okay, but from today, we are going to explore an alternative way to describe the semantics of program called denotational semantics. So denotational semantics is much more mathematical formalization so that it might be less familiar and less straightforward and less intuitive than operational semantics, but it will give you much more fundamental insight of program semantics and also provide many important and useful concepts which will be used throughout this lecture. Okay, then let's get started.
Okay, let's revisit these slides. As I earlier mentioned, there are multiple ways to formally define program language semantics. One of the most popular way is the operational semantics we learned in the last lecture. So another popular method is the denotational semantics. This method does not take care of how the result is computed, but instead it directly defines the meaning of programs as mathematical objects. So in the previous lecture, what does operation means? So the term operation makes sense only when we assume machines or other subjects to be operated for computation. So recall that we define big step operational semantics as proof. So actually proof is an operation, right? So recall that we define small step operational semantics as state transition. So what is transition? Transition is an operation. So we by default assume some machines and operations. Okay, when we define operational semantics of program. But here we want to find the mathematical object directly that corresponds to the semantics of a program without relying on any machines. So we are going to find the mathematical meaning of the program. So there's no state and no transition. Okay. Then what kind of mathematical objects will be the semantics of program? So intuitively, function will be the best choice, right? So we are going to define the semantics of program as a function from input state to output state. So the most important characteristics of denotational semantics is that the semantic definition is compositional, not inductive. That means that the semantics is solely determined by the semantics of each subcomponent, not that of itself. So we will use this notation that represents the semantic function for program P that maps input memory state to output memory state. Okay. Here again, the same simple imperative language. So we will define the denotational semantics of the program written in this language. Okay, then let's define semantic domains. We will also use the same semantic domains as before. So semantic domains describe set of semantic objects here. The memory is a mapping from X, which is the set of variables, to V, which is the set of values that consists of integers and booleans. Okay, here is an example. So notice that here we don't use arrow, but we use this equality, right? Which means that the semantics is not state transitions anymore. In the semantics of function program is a mathematical function that satisfies this equality. Okay. So actually, as you might already notice that we've already used this concept in the previous lecture when we defined the semantics function of expressions. The meaning of each expression is a function that takes a memory as an input and returns integer or boolean value. Here is we have the same definition of the arithmetic and boolean expressions. Okay. Okay, then let's define the semantic functions for commands now. So there are also not going to be difficult. The semantics of each command is a function that maps memories to memories. Okay. The semantics of this skip is a function. Actually, it is the identity function. So skip just returns the input memory as the output memory. Okay. And what about sequence? So the semantics of sequence is actually function composition, right? First, we apply the semantic function of the first subcommand to the input memory, and then we apply the semantic function to the second subcommand to the intermediate memory state. So the next is assignment and input commands. These are update function. So they update the value of x. They update the value of x to the semantics of the corresponding expressions. Or in this case, the value will be the output of the semantic function of expression, and in this case, n will be a value from outside. Okay, so the next is the semantic function of if command. This semantic function will be determined by the semantics of conditional expressions and also each subcommands. So if the semantic function of the conditional expression returns true, then we will define the semantics as that of the true branch, and otherwise the semantics of false branch. Okay. So far, what do you feel? So each definition is quite straightforward as before. I mean, here we have similar structure to the operational semantics, and everything is compositional so far, which means that the semantics of a command is mathematically defined by the semantics of each subcommand. Okay, so this is really compositional. And then let's talk about the semantics of while. So how can we define the semantics of while as a function? Okay, one possibility is we functions like this, which means that while command takes input memory and return an output memory. So far so good, and the output memory will be computed like this. Okay, first you apply the semantic function of the body here, and then you apply the semantic function for the whole while command again to get the output of the while statement. But notice that it is not really compositional. Okay, so it is not a direct function definition for the semantics of while, which means that it's not an explicit formula. It's just a recurrence relation in mathematics, right? So one analogy is here. Okay, I guess all of you are familiar with the Fibonacci function. So here is a common description of Fibonacci function, which is inductively described, which means that on the left hand side you use this function Fibo, on the right hand side you use this Fibo again. So that is an inductive definition of Fibonacci function, right? But here it does not tell you what the Fibonacci function is. It's just to tell you how to compute Fibonacci of n. Okay, so in this situation, what do we do usually? So we try to find a general term of this recurrence relation and define the function directly by using these general terms. Here is the general term of the Fibonacci function. This definition, as you can see, is definitely compositional. So this definition is compositional definition that explicitly tells you what Fibonacci of n is. Okay. But in general, finding such kinds of general terms of arbitrary functions is non-trivial. But semantic functions of computer programs have very special characteristics which will be described as follows. So let's first define this inductive definition as an equation. Okay, So that means that notice that we have the same component on the left hand side and right hand side of the equation, which is the semantics of while. Okay. Then we can simply rewrite this equation like this by introducing a function f here. Okay. And the definition of f is simply like this. As you can see, it is just a mathematical rewriting. Here I did not do anything special. So if you expand this equation with the definition of f, so you will get the original formula here. Okay. By the way, here for someone who is not familiar with the lambda notation, so here is the description. So this lambda notation just simply represent a function. So this notation f of x equals to blah blah is actually the same as f equals to lambda x blah blah. Okay. Okay, then what is the semantics of the loop? The semantics is defined as a solution of an equation. Okay, look at this equation. The semantics of while is actually equals to f of semantics of while itself. Okay, then if I slightly change the equation by substituting the semantics of while as x, then it becomes much more clear. So as you can see, x is a solution of this equation, which is that x means the semantics of y. Okay. Here, notice that nothing special here. So let's forget about the semantics part. And this kind of equation are just the usual things in high school mathematics, right? Which means that x is equals to fx and x is a solution of this function f. Okay, but especially this is not an arbitrary solution of this equation. This equation looks very special, which means that if we apply this function f to the solution x, okay, then it returns the solution x itself. Okay, this kind of x is called fixed point in mathematics. Okay, and then the semantics of while is a fixed point of function f. Okay, but mathematically a function might have multiple fixed points. So among them, we define the semantics of while as the least fixed point of the function f. Here we use this notation LFP, that means that the least fixed point. Okay, so then let's take a look at the whole definition of while semantics. So is this compositional? So there's no recurrence at all, right? So it is perfectly compositional. Okay.